Okay, so we are ready to start. Welcome everybody for today's webinar. This is the last of a series of a technical webinar LATI Tech Group offered to all our customers. Today we are going to talk about designing with thermally conductive materials, a design tutorial. We will use real case histories and geometries to discuss and talk about design tips and criteria in order to use the best this kind of materials. But first of all, let me introduce me. I'm Agnese Zappa. I work in the technical assistance team. I perform finite element analysis in what we call the co-design service. And I'm here today with my colleague Federico Basile. Federico Basile, would you like to introduce yourself?
Yes, thanks, Agnese. Good afternoon, everyone. Thanks for joining us to this webinar. My name is Federico Basile. I work in technical service team with Maria Agnese Zappa. I deal with providing technical support to customer, either pre-sales and post-sales, and as well as providing support, molding support for molding activity and troubleshooting during molding and so on.
So now we really would like to know what about you. Here we start this survey. What department do you work in? Please let us know in which department you work so that we know which kind of preparation you have. Okay, just gives few additional seconds for you to sign. Perfect. Just to share, to let you know which kind of audience we have. We have mainly people from sales and marketing. We have other people working in other kind of group, a 20%. If you want, you can write in the chat which kind of work you're doing. And also a number of people working in the R&D sector. So hello to everyone and welcome. Moving to the agenda. Today we will start with an introductory part which is composed by 3 parts: an introduction, a session where we will talk about heat transfer physics, an introduction of thermally conductive thermoplastics. So we will see which kind of products are present on the market and which are the main differences. Then we will go into the real core of this presentation with 2 sessions dedicated to design tips for heat transfer efficiency and for molding, and efficient molding of these materials. And then we will finish with real case histories. We will talk about the successful application of these materials so that you can have an idea. But first of all, when and why would you need to select this kind of materials, thermally conductive materials? Well, the situation, the sectors where you may need to select this kind of materials are a lot, starting from LED lighting to radiator, sensor, electric and electronic, and last but not least, the automotive, especially the electric one. In all this situation, you may need to manage a thermal power. For which reason it may be necessary to manage a thermal power? This is an example. And this is specific of the LED lighting sector. And you can see here how LED lifetime expectancy decreases as temperature rises in a specific area of the LED, which is called the junction temperature. It's not only a matter of lifetime, but also a functionality matter. So if temperature rises are too high, you may have a variation of the color of your LED, and you don't want your LED to have a different color than what you designed it for. Why preferring a thermally conductive compounds compared to traditional solutions, so aluminum and other metals, alloys, for instance? There are many reasons. The most important one to me is because it's lighter. Thermoplastic compounds, thermally conductive thermoplastics have a lower density, so you will obtain with the same geometry, with the same volume, part which is significantly lighter. And you can think about all the advantages of having a lighter component. Then there is a matter of cost reduction. This is correlated both to the cost per volume of material, but also the processing costs. So you can just think about the temperature which is required to melt this kind of material, which is maximum 300 degrees centigrade, compared to the minimum of 700 degrees for an aluminum. Then, because these kind of materials are injection moldable, you have a wide design flexibility, and so you can integrate a function in a singular component. The component is ready to be used as soon as it is extracted from the mold. Depending on the class of compound, you may have colorable version, so you may not need to paint it at all. Then you don't need to post-processing the component, to post-process the component as deflashing and machining, apart from the removal of the sprue and of the cold runners, for instance. Then the last aspect, which is nowadays more important, is the sustainability aspect, because all thermoplastics material are recyclable, potentially recyclable materials, and they may have also a lower impact towards the environment because of the lower processing temperature and processing energy required to create a component. Let's start to talk about heat transfer physics. Now we will talk about the mechanisms involved in heat transfer. We will use this geometry. It's a component by Hexagro Pro Tool Plastics, which is our customer champion, our last customer champion. And I invite you all to have a look to our last video, in which we talked about this case history in really deeply. So the first question you may have is, how is it possible that a component that was typically produced in aluminum, because you needed to dissipate heat, is now feasible with a thermoplastic compound, a conductive thermoplastic compound? We all know that the thermal conductivity of metals is quite high, the highest possible. And for aluminum, we have a value of 150 watt over meter Kelvin, while for our one among our highest performing compound, this polyamide with the 50% of graphite, the mean conductivity, the average conductivity is 10 watt over meter Kelvin, so magnitude order lower. How is it possible that the project is feasible? Here we have the results of the first feasibility study we performed on this geometry. And as you see, we obtained lower temperatures on the component made out of the thermoplastic materials. So how is it possible? This is possible because conduction is only one among the heat transfer mechanisms which are involved in the dissipation. So, talking deeper into this matter, conduction is a heat transfer mechanism which works inside the component. It is applied here Black arrows represent the heat transferred by conduction. We know that conduction depends on a parameter, which is the thermal conductivity. We already talked about it. This is a simple formula which represents how heat is extracted through conduction. Here we see that conduction K is here. The highest the conduction, the highest the quantity of heat which is extracted, which is transferred. We all know it, but this is just the first step. Moving to the second step, convection. Convection is a mechanism which is working between component and the ambient. Here we see it's represented by the light blue areas. It depends on how wide is the surface available for heat transfer. It depends also on a heat transfer coefficient in the medium, in the liquid, in the gas, in the cooling system, in the cooling liquid you may have around your component. And it depends whether the convection is natural or forced. This is a simple formula which describes how heat is extracted by convection. H is the heat transfer coefficient. A is the surface, how wide is the surface. The highest the A, the highest the quantity of heat which is transferred. Just to anticipate, our materials, thermoplastic, thermally conductive compounds, are working well only in natural convection regime, so not where it's designed a cooling system, for instance, as venting. Moving to the last mechanism, radiation. Radiation is the last mechanism. It works as a convection between component and ambient. Here it's represented by the orange area. It depends again on the surface, how wide is the surface available for heat transfer. It depends on a parameter which is called emissivity and on a geometric view factor. This is the formula which describes radiation. We see that emissivity is epsilon here in this formula. Epsilon, the emissivity depends on the color and on the surface finish. So then there is also A, which is again the surface, and B, which is the geometric factor. As you know, I think you noted it, in convection and in radiation, there is no material characteristics apart from the color. So that's why thermally conductive compounds may work in this kind of application, because conduction is only the first step of dissipation. Then there are the other two, and in some cases, they may be enough to dissipate heat as required. Now we can move with Federico to the thermally conductive materials. I'll leave you the stage.
Thanks, Agnese. Thanks for having showed us the principles we exploit for thermal dissipation management. Now we will jump into some details about thermoconductive materials. As maybe you already know, the standard polymers mainly used for injection molded, usually used for injection molded, have a thermal conductivity which ranges between 0.15 and 0.25 watt per meter Kelvin. This level of conductivity is not enough to be exploited in the management of heat dissipation. In order to enhance, increase the thermal conductivity, we need to add during the compounding process some some conductive fillers inside the resin. We have different kind of conductive fillers to use. The main ones are ceramic fillers, boron nitride, and graphite. Some of these fillers may be anisotropic. That means that the thermal conductivity varies depending on the direction we consider and we measure. Usually the value along in the longitudinal direction is higher than the value in the transversal direction of the fillers. This means that these fillers have anisotropic properties, not only thermal properties, but in general are anisotropic. And when during molding, they are subjected to orientations. The thermal conductivity increases linearly with the amount, with the percentage of fillers. Usually for anisotropic materials, the value measured on a molded sample in plane direction, in the direction of filling, it's much higher than through plane. Due to the orientation of the fillers. What kind of resin can be used for making these thermoconductive materials? Basically, any resin, either semi-crystalline and amorphous. But in the case of amorphous resins, we have some limitations in the maximum filler content due to some physical characteristic of amorphous polymers. The main filler used, as we anticipated, are graphite, ceramics, or boron nitride. They feature some differences. The graphite is an anisotropic, have anisotropic characteristics. It's electrically conductive and has an high aspect ratio, whereas the ceramic is isotropic. From a characteristic point of view, it's electrically insulative and has a low aspect ratio. This means that during molding there is no so much influence due to the orientation of the fillers. Boron nitride is something in between, in the sense that it's anisotropic, has an isotropic characteristic like graphite, but it's electrically insulative like other ceramic fillers. And this also has also an high aspect ratio. Here in LATI, the thermoconductive materials are identified by the family called LATI Condor. We have two main subfamilies, subcategory, LATI Condor GR, which feature graphites, and the LATI Condor CP, which features ceramic fillers. The LATI Condor featuring graphite have the best performance in terms of thermal conductivity, and they are electrically conductive also. Whereas the ceramic versions, they have also a good thermal performance, but are electrically insulative, so they can be used in application where has to be guaranteed the electrical insulation. Plus, another advantage of this family is that can be colored in some color shades, and some self-extinguish flame retardant version can be tailor-made.
So now we arrived to the real core of this presentation, design tips for heat transfer efficiency. These design tips are those we typically suggest to our customers in the feasibility study. We focus in this presentation on three main points. The first one is the design optimization for heat transfer to ambient. The second one is the design optimization for the heat flow. And the third one is the design optimization for the conduction inside the part. The first topic is actually valid also for metallic solutions, so it's nothing new in this sense, while the second and the third point are kind of peculiar to thermoplastic compounds, specifically to those with anisotropic behavior as graphite. Let's start with the first topic. We will use again the geometry by hexagram. As we saw, the convection and the radiation is enhanced as soon as the surface is increased. So, which is the simplest way to increase the surface? By adding fins or other kind of geometries. So here an example, on the left was the original geometry, on the right that with the addition of fins. This way it was possible to increase by 25% the surface available for convection and radiation. And we see here how different is the result of the thermal study on these two geometries. In this case, the limit temperature was 65 degrees. In fact, this part was, it was possible for people to touch it, and the customer didn't want anyone to get burned. So 65 degrees is the limit temperature below which you don't get burned if you touch it. And as you see on the left, the temperature outside that hexagonal shape, which is on top of the dissipator, of the heat sink, was more than 68 degrees. By just adding fins, the temperature dropped to 63 degrees. So this made the difference between a project which was not feasible before and became feasible after the addition of fins. Fins or pins? There are many options, really, a lot of geometries possible. This is just an example with the same hindrance of the geometry. You will obtain, of course, different results. Generally speaking, pins are more efficient compared to fins, but they may be more difficult to manage. One of the reasons is that the contribution of radiation is lower for fins. In fact, as you can see from the picture on the right, all the fins are radiating the one on the other when they are facing. And so the contribution there of radiation is zero. You can see in these pictures that you can really design, you have a wide flexibility in the design, and this is thanks to the fact that you can injection mold this component. In general, the higher the surface area, the higher the dissipation, as we understood. And take care, avoid closed cells, because they will reduce the dissipation efficiency. And this is because air will find difficulties in flowing, and so the convection is hindered in somehow. Moving to the second point, design optimization for the heat flow. This is something new because we know that metals, they have high thermal conductivity, so they become hot with the same temperature all over the component. And this is not the same with thermally conductive compounds. So you will have a difference if you will apply the heat on, for instance, on the square on the left with the 2,300 millimeters square millimeter area, and the circle surface on the bottom. Here we see the results of the thermal simulation we obtained, keeping the same parameters fixed, the same thermal power, the same temperature, the same kind of convection radiation. You see how the result is changing with the increase of the 30% of the surface. You reduce the temperature on component, and this means that the component is dissipating better. That's because you decrease the heat flow on the surface, and so you help the material to transfer heat to the area where there is convection and radiation, and the component will be more efficient. How? Of course, exploiting the best of the geometry. Then it's important to be sure that there is an optimum contact between the heating system and the heat sink, and this may be assured by selecting conductive pads and tapes. And also you can think about using a spreader. Here you see on the right the spreader. It helps distributing better the heat on the component. Take care about the flatness of the surface, because if there is any warpage, you will have a lower real contact surface, and so the dissipator efficiency will be lower. This is because where there is air, heat is not transferred, and so the real contact area will be lower than the ideal one, that one you thought that was. This is particularly important in case you are using a spreader, because you won't even notice it because it will be below the spreader. How is it possible to evaluate the flatness of the surface? This is the result of a filling simulation, the last step, which is the warpage. We can have a look to how the part will warp after molding, and there is also a result which is called the flatness. You can just consider that the best flatness is around 0.1. This means that all points on this surface deviate from the ideal surface of maximum 0.05 millimeters in both directions. Flatness can be also worse because of another effect you may have with this kind of components, which is called sink marks. We typically suggest our customers to design fins and pin in order to have the thickness at the base lower than the thickness of the base itself. You see here, D should be lower than 2/3 of D. This is because where you have a higher thickness, you will have a higher volumetric shrinkage, and the differences in volumetric shrinkages will cause difference in you will have a warpage. So here we see the simulation on the center and the picture of the component after molding on the right. You see that sink marks are really visible, and this will cause the real contact area to be lower than the expected contact area. The last topic we will talk about is the design optimization for the conduction inside the part. For this, we wanted to think about the thickness, and in particular, the thickness of the base of an heat sink. You see here on the top the original geometry. We doubled the base thickness, and we had a look to the difference. So we performed a filling simulation, and we obtained the flake orientation tensor in order to see which was the difference between the two situations. We see here on the left that because of the lower thickness of the base, we will have a higher orientation of the flakes in the in-plane direction, while in the more thick base component, the orientation will be, the average orientation will be lower. This has a direct effect on the local conductivity of material, because we know that the highest the orientation, the highest the longitudinal conductivity, and the lowest the transversal conductivity. As soon as the thickness increases, the longitudinal conductivity decreases, but transversal conductivity increases. And in some cases, you may need that the transversal conductivity is higher. So depending on the situation, and typically you want heat to be transferred efficiently from the heating source to the surface, so to the fins, so in the transversal direction. A higher base thickness helps increasing the average thermal conductivity in order to exploit the best of this material. This is, sorry, I forgot to tell, this is of course related to anisotropic fillers as graphite. We see here the results of the thermal simulation we obtained using the flake orientation tensor, and just by doubling the base thickness, we obtain a decrease in temperature by 10 degrees centigrade. So it may be relevant. We now move to the design tips for molding process optimization.
Thanks, Agnese. Yes, thanks for having showed us some tips about the optimization of the heat transfer from the heat sink to the environment. Now we'll have a look at something similar about molding process. Which aspects we need to focus on when it comes to mold this kind of materials? The same aspects which apply, we consider in the molding of standard thermoplastic compound has to be considered, but some features require special care. We need to start from considering that all the decision taken in a particular stage of design will then have an impact on the next ones. So we usually start from designing a component from its geometry based on its functionality, but often or sometimes we let's say forgot to take into account how the geometry of the parts will affect then the molding process. So we need to think about this from the beginning. Then based on the parts geometry, we need to choose a proper injection system. This will determine the window of molding parameters we will have at our disposal to manage any eventual variation, for example, in terms of materials fluidity from one batch to another, and so on. And the molding parameters should, let's say, be the results of the choice of the material and the injection system, and this couple of from these two variables, and not to let's say chase any eventual errors and defect coming from the past the past steps. The two peculiar characteristics we need to keep in mind when molding these materials are the higher thermal conductivity compared to standard thermoplastic compounds, and the higher viscosity. Starting from general design tips which apply not only in the case of this material but in general in injection molding. The first one is to avoid abrupt thickness variations. This because it leads to different kind of defects. The first one is might be anesthetic defects due to the variation of flow speed at the transition of the thickness and correspondence of the thickness variations. The second one is the sigmas due to a different volumetric strain gauge between the thickest part and the thinner one. And also deformations, also due to the different volumetric strain gauge of the two areas having a different thickness. Another one is to avoid sharp angles. This because when we have sharp angles, it leads to shear stress in the material during molding and to stress concentration in the molded parts. So it's better to implement a proper fillet radius. It has to be the fillet radius has to be chosen on the basis of the thickness or the diameter of the area. The idea behind it is to keep as constant as possible the section upstream and downstream the corner. Then another tips, important tips, is to use inadequate draft angles. This because these materials are heavily charged, filled with fillers, conductive fillers, and may result a bit brittle and feature a quite low strain gauge. So there might be some problems of during extraction. Generally, for the thermoplastic compounds, depending on the level of reinforcement or amount of filler, inadequate draft angles might be in between 1 and 2 degrees, but for thermoconductive grades we suggest to apply at least 1.5 degree, adding an extra degree each 25 millimeters, more or less 25-30 millimeters of parts depth. Then, in case there is some texture on the mold, we need to consider to add another extra 1 degree for each 0.025 millimeter of texture. So yeah, the reason, because the reason of this is because, as we said, this material have a limited strain gauge, a limited tenacity, and in the case of, in the specific case of heat sinks and dissipator, where it's present, where there are some fins on pins, we need to optimize also the ratio between the length and the width of the fins or the pins, due to the risk of ruptures during ejection. Another point to consider is to evaluate, to avoid the long flow path. This because of the high viscosity of the material, which lead to an high pressure drop and require an injection pressure. So depending on the length and on the thickness of the section, we might have a certain level of pressure drop. Usually doubling the length, we will have a doubling of the pressure drop, whereas halving the diameter or the thickness, we may have pressure drops which jumps to 8 to 16 times the first one. One very important aspect to keep in mind is that the melt temperature during molding, during the filling phase, starts to decrease along the way during the flow, during the path to the cavity, and it does not start in the moment we set the cooling phase on the machine. So the decreasing of the temperature causes an increase of viscosity of material, and this phenomena is more evident with thermally conductive materials, since they cool down much faster than standard grades. How much the melt temperature can decrease along the flow paths? Since we may think that there might not be so big variations due to the short filling time usually needed for filling a molded component. But here in this example, from this example of a simulation, we can see that the temperature difference for this material is almost 30 degrees between one area and the hottest area and the coldest area of these molded parts in just 2.3 seconds of filling time. This may lead to different effects on during molding. The first one is filling difficulties. Indeed, we may have, if the melt temperatures decreases significantly, we may have some difficulties to reach the farthest area of the mold or to fill the thinnest sections. Another aspect is that in case there are knit lines, the two flow fronts which join in this area may not be so strong, because the two flow fronts joins together at a too low temperature. Then another aspect is that is about the planarity deformation. Areas having a different temperatures feature a different volumetric shrinkage, and this will result in deformation or in not perfect planarity. Then another aspect to focus on is the gate dimensioning. Why? Because due to the high thermal diffusivity and thermal conductivity of these compounds, we have at our disposal a much shorter time to properly inject and pack the molded parts, because before the gate freezes. Indeed, here, just to give you an idea of the different cooling time between a polyamide 6 50% glass fiber and a polyamide 6 with 50% graphite, we will apply a simple formula which can give us an estimation of the time needed to reach the ejection temperature. For simplicity, we will apply the same melt temperature and the same injection temperature to have a better comparison. And applying this formula, we'll see that an approximated cooling time in case of polyamide 6 with the glass fiber is about 4 seconds, 4.2 seconds. In case of the material featuring graphite, we have here a value which is 0.25, is about 16 times lower. So we have much less time at our disposal to complete, to properly inject and pack and complete the packing phase. The cooling time of the thinner sections and the gate, the dimension of the gate, so dictate the maximum packing time. Which is the ideal gate dimension? The gate dimension should be defined not only on the basis of the thickness of the parts at the gating location, as sometimes is done, but to evaluate it considering also the parameters like the cavity volume, the flow length, the flow rate, and so on. The idea is the aim of a proper dimensioned gate is to guarantee a proper flow area which allow a proper filling and packing of the parts. In case of a rectangular edge gate, for example, the gate thickness has to be between 60 and 70% of the gate of the parts thickness at the gating location, and with this parameter, with the gate thickness, we have more, let's say, constraint because it dictates the packing time. Then to reach the proper flow area, we can, let's say, play with the gate width once the gate thickness has been defined. But we have to also not neglect the fact that doubling or increasing or doubling the flow area will lead to a decrease of the flow speed. So if we double the flow area, the flow speed will be the half. So the gate has not to be neither over dimensioned, because this may lead to other problems due to a lower flow speed. And then another point is to evaluate carefully where to place the gates and the number. Indeed, a different position, different numbers of gates may lead to different results in terms of shrinkage, different deformations of the molded parts, because it has an impact on the packing efficiency, on the pressure drop, and so on. Here we give you as an example the filling time of same parts injected in one case with a single gate placed in the center of the parts, and in the other case with a multi-gate. The difference here, as we can see, of injection time needed is about a 50% difference between one and another. So this is the first difference we may immediately see. Then another difference is pressure inside the cavity. Here is reported as example the same component of the previous slide, injected with the same system, single gate and multi-gate, and as we can see here, we have a really quite a significant difference of pressure inside the cavity at the switchover time. This means that the pressure in the case of a multi-gate, which is almost 3 times the first case, in the case of the multi-gate choices, will have a much better pressure transmissions inside the cavity. Then the choice of the gate and the numbers affects also the filler's orientations, in case, which is particularly critical in case of anisotropic fillers. And as Agnese first explained earlier, this will determine the thermal performance of the parts.
Thank you, Federico. We arrived finally to the last part of this presentation. So we start with the first case history. Now we are all familiar with this part, with the hexagro part. This is a heat sink for a living farming tree. The project started with a aluminum replacement. We selected a material which is a polyamide 6 with the 50% of graphite. This allowed to obtain a part which is significantly lighter compared to the aluminum one. Then it also allowed to create an intricate design, something which is more similar to the geometry they wanted to have. You can imagine the previous heatsink in aluminum was a simple geometry taken from the market. In this way, it was possible for them to design the part to be as they wanted. With this part, they were also able to integrate the functionality of many different parts. And the component is ready for use without any post-processing. As you can see the part on the bottom right, this is how it is ejected from the mold, apart from removing the cold runner, the sprue. Part is like this, so ready to be used.
This other example is an heatsink spotlight, which is part of a series of different heatsinks, which differ from the thermal management point of view. This is something in between 500 and 400 lumen. It's a polyamide 6 with 50% graphite. And yeah, the advantage of choosing this material was, beside the lower weight compared to aluminum, also the anti-static properties, which allow to dissipate the electrostatic charge on the surface and prevent the accumulation of dust on the surface, on top of the surface. And last but not least, the design flexibility. Usually this kind of dissipators have a quite complex design.
This case history is again a spotlight, but a significantly different one, because this is an industrial spotlight. The thermal power to be managed was really huge, really high. This is an aluminum replacement project, and customer wanted the part to be white, so colored. So we selected a polyamide 6 with the 70% of graphite. This is the compound which offers the top thermal conductivity. As Federico explained, graphite-filled materials are also electrically conductive, and this allowed epoxy powder painting and also the following curing process. The component is really significantly lighter compared to the original one, and also it works in outdoor, so it's outdoor resistant.
This other case history is about design lighting for a showroom of a very important automotive brand. This component made with our LATI conductor was the heat sink for the LED light. Was a polyamide 6 with 50% mineral filler and halogen-free flame retardant. So, as we said before, this material featuring ceramic fillers can be made also flame retardant. The advantage was the lightweight, the white color, and yeah, the design freedom.
Now we move to a case history from a different sector to the compared to the LED lighting, and this component is on the automotive field. For the automotive field, it's an electronic vacuum pump housing. It's an aluminum replacement, and we selected a polyamide 6 featuring both graphite and glass fiber. So this way it was possible both to dissipate heat, but also to have a component which is resistant to vibration, to the vibration which are typical of the automotive field.
This other example is an alcohol test heating cartridge, and for an alcohol test system. The material employed here is a polyamide, polypropylene, sorry, with 70% graphite. And the peculiarity of this application is that since the material featuring graphite is also electrically conductive, the component itself works either as a dissipator, thermal dissipator, but also as a resistor. So applying a voltage, a differential voltage, by Joule effect, it will heat up, and then the heat will be spread towards the inner part of this component, where is placed the sample holder. The sample holder to analyze the sample to be analyzed.
The last case history is this outdoor spotlight. In this case, we selected a polyamide 6 with ceramic filler, a self-extinguishing version, because it was not necessary to have a high thermal conductivity, but electrically insulate. The material had to be electrically insulative and self-extinguishing, as already told. And also, they expected it to be not excessively brittle. So here we arrived to the end of this presentation, and we can start a quick survey. So please let us know what was the most interesting topic for you. Okay, thank you. I'm just giving a few additional seconds for you to vote. Okay, I can show you. You really liked my part, design tips for heat transfer efficiency, so I'm glad.
Good done, Agnese.
Thank you. Good done, you too, Federico. So, unfortunately, we don't have any time to answer to your question, but you can leave your question in the section in the box below. In any case, we will answer to your question by email, and we will also share this presentation and the link to the video, to the registration of this session. We are taking this opportunity to wish you all a happy winter holidays from all the LATI Tech team. See you next year, and thank you all for dedicating your time to us.
Thanks for joining our webinar. See you next webinar.
See you next time. Bye.
Bye.